Remember some things we already know about the equations for circles and maybe extend it like a very tiny bit. So let's start with the most familiar circle, the unit circle. Something that you know already. Here, let me draw this bigger actually. Okay, there we go. So you remember when I say the unit circle, what I mean is a circle of radius 1 centered at the origin. So here's the unit circle. If this is an arbitrary point on the perimeter of the circle at coordinates x, y, you know that the x is actually describing this side length. The x is describing this side length. I don't know what's happening to me. Y is describing that side length. And because this is a right angle, the Pythagorean theorem tells you that x squared plus y squared equals 1 squared, which is the same thing as 1. And you know that this equation describes every single point on this entire circle. It doesn't matter where I draw it. Even if I draw it down here, you might think that this has a negative y coordinate. But if you imagine squaring your y coordinate, it becomes positive, which is the same as describing the length of that side. Okay, so now let's see if we can recall the equations for circles that are transformations of this one. So first, let's make it a larger circle. What if instead of radius 1, we make it radius, 7? So now what we know is x squared plus y squared equals 7 squared. And I think the best thing to do is going to be to generalize it. So let's not use a specific number. Let's just call this a circle radius r. So again, Pythagorean theorem, x squared plus y squared should be, you guessed it, r squared. A different form of this equation, which you see periodically in calculus, and it's important to recognize it for what it is what you get if you try and solve this for y. So if I subtract x squared, from both sides of the equation, I've got y squared equals r squared minus x squared. And then if I take the square root, that gives me y equals plus or minus square root of r squared minus x squared. So that's the general form, but remember r is the radius. So this could look like a whole bunch of things in actual practice when you encounter it. So like what if you saw something that looked like minus root 7 minus x squared? You should look at that and say, aha, wait a minute. I've got the square root of a number minus x squared. That is probably part of a circle. The plus or minus refers to the top half and the bottom half, because remember this is a y coordinate. So a positive y coordinate would be like the top half of a circle. The negative y coordinate would be like the equivalent bottom half of the circle, the reflected bottom half of the circle. So if I've got this equation, that's like the bottom half of a circle like this, whose radius is what? Think about it for a second. Whose radius would be square root 7. Because remember, whatever the number is, that came from this r squared term. So if this is a square number like 16, then we know that the radius was really 4. But because this number isn't a square number, the radius of the circle is just the square root of that number. So this right here is actually like literally the graph of this. And these are closed circles here because it's okay to have a 0 under the radical, under the square root. What if I had like square root of 100 minus x squared? Again, you look at that and you think, aha, it's a positive root, so that's the upper half of the circle. This one's got radius 10. Well, you can't really see it there, but radius 10. Okay, so that's going to be an important thing, is being able to see things that look like this and say, aha, that's a circle. Okay, let's transform it again. What if we were going to take our circle and shift it right by a certain amount and up by a certain amount? So to shift it right, you know that you substitute x for x minus some value. Let's call it maybe a. And then if I'm going to shift by the y value, I'll replace y with y minus some value. So if I take my original equation here and I replace x with something like x minus 3, and I replace y with something like y minus 1, that's my original circle, except now I've shifted it right by 3 and up by 1. And if we make it equal to, say, 3, that would be a circle whose radius is square root of 3 that's been shifted right, and up. So let's go ahead and make this fully general again. Instead of shifting it right by 3, let's shift it right by A. Instead of shifting it up by 1, let's shift it up by B. And like this is an important form to recognize also, and hopefully you would recognize that as a transformed circle. But usually if you're working with some algebraic equation, you're not going to see it in this form. You're going to see it multiplied out entirely like this. So you'll see, some big mess here, but it's got an x squared and it's got a y squared, and those are the highest degree terms for both x and y. And then it'll probably have some other stuff. It may not have a 2 here. The 2 came because I expanded this. What it might actually look like is more something like this. So like I said, looks ugly just because you're not used to seeing equations with so many terms. But you notice you've got a quadratic in x and a quadratic in y. And this is, I said before, completing the square wasn't really about solving equations. This is why. Completing the square is useful for simplifying equations. So if you're able to complete the square here, you can turn it into a form that will tell you more about the circle that this really is. So come back in the next video and we'll complete the square for this sort of thing.